students, it's Ms. Culver. We are working on section 1.3 today, and we are starting with A. We have broken 1.3 into 3 sections. There'll be an A, B, and a C because there's a lot going on in 1.3 and it's all really very important. Today, you'll be happy to know 1.3A, we will be analyzing limits analytically, and we will be doing the easy ones today. So let's find out what that means. The first thing I want to tell you, I'm just going to step in front of the camera here, is when we did section 1.2, we were looking at limits numerically by using charts of numbers, and we were looking at limits graphically by looking at graphs. And the point I was trying to make is that when you are evaluating a limit as x approaches a certain c, that it is totally a separate issue from what the value of that function is right at that c. Sometimes the limit exists and the value of the function does not. Sometimes it's the opposite. Sometimes the limit exists and it equals the value of the function. But my point was that we have to evaluate those two items separately. What we're actually going to be looking at today, though, is you'll be glad to know that very often when you are evaluating a limit as x approaches c, that you actually can use the value of the function at that c. It actually does solve the limit. That happens a lot. So when does that happen is what we need to know. Here's when this happens. We are going to be evaluating properties of limits, starting reading the blue here, where functions are continuous. What a continuous function is meaning you can draw them continuously. It's that easy. If you put your pencil to the paper, you can draw a function continuously. Now, what this means in calculus speak is, why can you draw that function continuously? You can because it's smooth. Its limit as x approaches c from both sides of x heads towards a y value, and at that x, it hits that value. It's smooth. That happens a lot. So let's take a look. These functions include polynomials. Here's a line. I can draw a line continuously, a parabola, a cubic function. This is also true for sine and cosine. You can draw them continuously. They, in case you forget, take a wave formation. Exponential functions have that nice curve of growth or decay. They also include logarithmic functions, which are the inverses of exponential functions, and rational functions, which tend to have two curved branches. Now here you may say, well, but Ms. Culver, I can't actually draw this function continuously without lifting my pencil from the paper to make two separate branches. That's why for rational functions we have to say that they are continuous on their domain where they are defined. So right here at this x value, you're right, there's no value of y. But if I'm drawing either one of these branches, I can draw them continuously. So we can apply these properties of limits below in purple here because they are also properties of functions. Both a limit and a function, if it's approaching x or you're evaluating the function at x, produces a y value. So these properties are actually properties of functions. We can apply them to limits because they are the same. Here with the star, drawing continuously means for as each x approaches c, the graph approaches a y value and attains that y value at x equals c. It heads towards it and hits it. So the limit as x approaches c of f of x does equal the value of the function at that c. Yesterday I said you had to separate those two things and look at them separately. There's a lot of smooth functions where this actually is true. So what we're going to look at today is, in green, number one here, is evaluating a limit using direct substitution. The first thing you will always do, even as we head towards that final exam, is if you were offered a limit and asked to evaluate it as x approaches c, see if you can put that c into the function and produce a value. If you can, you have solved the limit. If you can't, which happens a lot, we have a little bit more work to do, like we may have to factor or divide. We may have to rationalize the numerator. That's right, you're used to rationalizing the denominator. We might have to rationalize the numerator. That's later in section 1.3. Okay, so direct substitution in green. If inputting an x value of c into the function, when you are asked to solve the limit, produces a y value, then you have solved the limit. So let's take a look in purple at what that means. I will be using a little whiteboard to help us too for the first 4 problems, and then we'll just roll from there. So on A, the limit as x approaches a of x to the n equals a to the n. Notice what they've done here is I've said if you've been offered a limit as x approaches a value, if you can put that a in for the x and actually produce a y value, a limit, you're done, you solved it. So here's an example. The limit as x approaches 2 of x cubed. Let's put the 2 in to the function. Can I solve this? Yes, I can. It's 8. That means that the limit is solved. I'd like you to see it another way. This function right here, x cubed, let's go ahead and draw it. On my little whiteboard over here, notice I can draw it continuously. It's what we call a well-behaved function. Here's 1, here's 2. At 2, we know that x cubed has a y value of 8. In other words, as x approaches 2 from the left and the right, the value of the function approaches 8 and it hits it right at 2. Our limit is solved. Let's take a look at B. The limit as x approaches a of c equals c. What does this mean? Here's an example. The limit as x approaches 15 of the function 3 is 3. C equals c. All right, what does that mean? Let's go to the board. Let's actually draw this function. We can draw the function 3. It's a horizontal line where y equals 3. There we go. 1, 2, 3. There we go. There's the function 3. As x approaches 15, doesn't the value of the function always stay 3? That's what we just said here algebraically. Here it is graphically. Okay. Super easy. Let's go to C. The limit as x approaches a of x is a, right? So again, we're using direct substitution. Let's put that a in for x and it produces an a. What does this mean? Let's try an example. The limit as x approaches 10 of x is 10. So let's take a look. You know what this function looks like. The y equals x line, right? That's that diagonal that cuts right across the first and the third quadrants. Here it is. There is the function y equals x graphically. So of course, as I approach 10, so does the function because it's the y equals x line. There we go. We evaluated the limit by direct substitution. Okay, let's take a look at D. The limit as x approaches a of some constant times a function is equal to, you can actually bring the constant on the outside and multiply it by the rest of the limit. So let's take a look at this. The limit as x approaches 2 of the function 3x. Let's see if we can use direct substitution. Let's just put that 2 in for x. Sure enough, 3 times 2 equals 6. Let's see if that's the same as we said we can bring this constant on the outside of the limit and evaluate the rest of it. We brought the 3 out, and we will multiply it by the rest of the limit. We have a 3, and we already know what the limit as x approaches 2 of the function x is, right? We already drew it over here. As x approaches 2, so does y. It's the y equals x line. There we go. That property is true. So the rest that we have looks fairly complicated, but starting at E, but it's all based on what we already have over here. So we won't need to use our board anymore. So let's take a look. The limit as x approaches A of 2 functions being added or subtracted is simply, you can take the limit of the first function, add the limit of the second function, and add or subtract those limits. Again, the reason we can do that is that the properties of functions produce y values, and so do the limits, so we can apply these properties. Let's take a look over here. That means the limit as x approaches 2 of x plus x squared. Let's go ahead and use direct substitution to solve this. That would be 6. And when we look above, it means that we could take the limit as x approaches 2 of x and the limit as x approaches 2 of x squared separately, and then add the limits, right? Direct substitution here is a 2. Direct substitution here, 2 squared is 4. Sure enough, that property is true. It also means on F, if we are asked to find the limit as x approaches A of 2 functions being multiplied, we can find the limit of the first function, the limit of the second function, and that will be equal to the first expression. So take a look here. We did the limit as x approaches 2 of x times x squared. Let's use direct substitution here, right? And we get an 8. There we go. And that should equal the limit of the limits of the 2 functions being multiplied. Let's take a look. The limit as x approaches 2 of x, we've worked with that function a lot, is 2, times the limit as x approaches 2 of x squared is a 4, and of course we get the same value. Let's take a look at G. Of course, this means if we divide, if we have the limit as x approaches A of 2 functions being divided, it means we can take the limit of the function in the numerator, the limit of the function in the denominator. We just can't have that denominator equal 0. That can't happen. And the first expression would be equal to the second. So let's take a look and see if that works. The limit as x approaches 3 of x plus 3 over x plus 6. Let's evaluate using direct substitution. That would be 6 over 9, or 2/3. Let's do the limit of the numerator and denominator separately and see if we get the same answer. Direct substitution in the numerator is still the 6. Direct substitution in the denominator is still the 9, and we get 2/3. Last one. So if you remember composition of functions, if you have the limit as x approaches A of one function composed of another, what you can do, notice f is the outside function, g is the inside function. What you can do, keep the f on the outside and take the limit of the inside function, and these two expressions will be equal to each other. Let's take a look. Last one. The limit as x approaches 2 of in parentheses x plus 1 squared. Notice I have a composition of functions. I have the line x plus 1 inside the squaring function. All we have to do, whenever you are offered a limit, see if direct substitution works first, right? Super easy. Let's put a 2 in. 2 plus 1 is 3, squared is 9. Okay? Apparently, according to this property, if I put the function on the outside, right, our squaring was the outside function working on the inside function of x plus 1. So if I have the outside function and take the limit of the inside function, I should still get a 9. So let's take a look. Let's do the limit on the inside. The limit as x approaches 2 of x plus 1. Let's use direct substitution. That's a 3, right? And 3 squared again is 9. So, of course, because it's calculus, it looks super complicated, but it's all such easy substitution. So, in general, on 1.3a today, you will have really easy limits to solve. Try direct substitution of that x value first, and most often you will get a value out for the limit. Okay? So that will always be the first thing you do all through our course when you are asked to evaluate a limit. So thanks for looking at properties of limits with me today, and have a good day.